Welcome back to ECE 442-542. This is not a repeat lecture, I hope. I hope I don't have to repeat this one, but I did repeat the other one that was on Monday, so if you want to see it without any audio and then watch it again with audio, you're welcome to do that, but I think you have better things to do. They're probably not quite the same, but they're labeled the same in D2L, except they have different dates on them. The more current or recent date is the one with audio, the one that occurred yesterday on the 28th of April. It may not be as entertaining. Maybe none of them are when you're just listening. Maybe none of them are when you're in class. But I wasn't with an audience when I recorded yesterday, so there's no give and take with the audience on yesterday's. As a reminder, homework number 7 is due Friday. Your project, if you are in 542, is due next Wednesday, a week from today. Homework number 8, which is available for extra credit, although the material, some of that will be on the final exam. The points on homework 8 are optional, but the material content is not optional when you get to the final. Meaning you need to know that material. Whether you turn it in for a homework extra credit point is up to you, but you will be responsible for that material content-wise on the final exam. Is that clear? And I would appreciate, I need to look, maybe I will before Monday's class, at the participation, the fraction of the class that has and has not performed the TCEs. Now I feel a little bit more comfortable with that because I'm not handing out exam 3 now, but you've already seen exam 3. And the final exam, wow, is 2 weeks from tomorrow. Is that correct? Tomorrow is April 30th. 2 weeks from that date is the last day of finals. I know it seems like the world is coming to an end, but it will all be over in 2 weeks for those of you that are seniors, in terms of what all the deadlines that you have coming up between now and then. Good luck with all of that, and hopefully you will still be with us for Thursday's final. And that's not a normal Monday, Wednesday, and it's a different time. It's at 1 o'clock. So I'm announcing that not only for your information, but also to remind me when I need to show up. That will be in this class, the final exam. Unless you're taking this class remotely, you don't have to come to Tucson to take the exam. Before we get into the goals, let me just give you some abbreviations that I will be using from now until the end of the semester, dealing with state space representations, and this way you can text this to mom and dad if you want. They'll know what you're talking about. If you start saying capital CTSS, they'll know that's continuous time state space. Or if you put a DTSS, that will be discrete time state space. We are now going to get into a new way of doing controller design, and I'm entitling this the next 3 lectures, that's all that are remaining for the semester. We will now be playing in the state space. We'll be doing our design via state space representations. And to do that, what we want to get comfortable with or remind ourselves of is how do we obtain these state space representations. And we've already talked a little bit about that. I gave you one method of taking a state space representation in continuous time into a discrete time state space representation, but that was a year ago that I provided that material. You probably didn't watch it a year ago, but that's lecture 4.3a and b. You were asked to do that earlier in the semester, but if you want to go back to that, that's where you would find it, is in lecture 4.3a and b. Today we will talk a little bit about the summary square of zero-order hold equivalence. How do we relate all of these different representations to discrete time state space? And today we will take a transfer function, g of z, and place that into a state space representation. Meaning, you should be very comfortable obtaining a capital G of z, or if I hand you a capital G of z, can you now produce a state space representation? You need to be able to do that to follow along with the remaining material that we're going to talk about in the next 3 lectures. And the first thing that we will talk about is state feedback. And now, what do they say when, I've forgotten the wording, but it's basically an overused notation in software or in MATLAB. If you can use something in many different ways, what's the description? Pardon? They have a particular word for it, and it's escaping me now, but it's overused, basically. Here, capital K is not a scalar. It can represent a matrix when we're doing state space representation. And the reason I am using L to indicate my index of time is because I may use little n to indicate the size of my state vector x. I don't want to confuse you, but I may do that anyway. I may say x of n. That just means x at time step n. It doesn't mean the length of the state vector. But so there you'll have to sort of keep track of what I'm meaning and when I'm meaning. If we had a single input system, U, the input, is a scalar. It's 1 by 1. U of L is just the sequence of inputs that you apply to your system. If U is a scalar, 1 by 1, and your state vector x, let's say you have 10 state vectors, x is now 10 rows tall and 1 column wide. What would K be? The state feedback gain matrix. Capital K, what is that? And I'll tell you it's not a scalar. What are the dimensions on K? Do you see what I'm trying to get you to see? Or do you understand what I'm trying to get you to see? U, the input, is 1 by 1. You're trying to make this product of K with X become a scalar. And X is tall and thin. You need to pre-multiply that by a row vector that's 1 row tall and 10 columns wide. It's now compatible with X, and when you multiply K with X, it collapses down. You have the first component of K times the first state component, X sub 1, added to K sub 2 times X sub 2. Those all collapse down. You now have a scalar on the right. K is a matrix that's 1 by 10 if X is a 10 by 1 state vector. That will become, I think, more comfortable when we start going through some examples. We will look at what this state space feedback or full state feedback looks like in a block diagram. We're essentially taking all of the state variables and feeding those back into creating our input command, little u of L. And we'll give a process for designing K. Then there are some issues that you need to be aware of when you're looking at designing full state feedback. One is that the full state vector, all 10 of those elements, you're assuming are available for you to measure. You can scale those measured values and feed those back. Those are all past tense, meaning they're measured, they're scaled, and they're fed back into the system to make up an input command. And the reason we're doing full state feedback is to change the dynamics. We've been changing the system dynamics with a transfer function controller, capital C of Z. Now we're changing that with the state feedback vector, capital K. That's the idea behind full state feedback. We'll talk about these, but the system will need to be controllable. We will be building what will be called regulators, and then we will say, wait a minute, we want to inject a reference input, and what does that mean? Well, we'll get to that, or that will, I hope, become clear. But when we do apply a reference, an external reference input with full state feedback, we need to be aware that it's very sensitive, or can be very sensitive, to system uncertainties or changes in our plant. Can think of a mass spring damper system. Maybe your spring constant is not very well known, or maybe your mass changes, or maybe the damping changes. That may really impact your behavior with full state feedback. Because in full state feedback, you're assuming you know very accurately your system. Let's get into some of this. Just as a reminder, here is what we're dealing with. Here is our model. Here is our discrete time state space system representation. Little x is actually a tall, thin vector, and it's n rows tall. Nevada tall. Let's say it's 10. Then in general, your input could be Michigan tall. You could have 4 inputs, maybe. Little m would be 4. Your output, maybe you have 3 different outputs that you're measuring. What did I use? Q is now is 3. Little q is 3. What's the dimension on capital H? Your output matrix, if you have 10 states, 4 inputs, and 3 outputs. What's capital H dimensionally? Is it clear what I'm asking? H has to be compatible with all of those dimensions I just gave you. And little x, I just told you, was 10 rows tall. And these are now matrix products. And if x is 10 rows tall, how many columns do you know H has to have for HX to be consistent or a compatible matrix operation? It has to have 10 columns. H, you know, is 10 columns wide. How tall is the H matrix? It depends on how many outputs we have, and if I told you I had 3 separate outputs, maybe I'm measuring a voltage, maybe I'm measuring a position, maybe I'm measuring a pressure from this dynamical system, then I have 3 separate outputs. Y, the vector Y, the output vector is 3 rows tall. It's just 1 column wide because it was, whatever I said, voltage, position, and pressure. That's how tall Y is, and H has to be compatible with Y when you multiply H with X. H is 10 columns wide, it's 3 rows tall. H is a 3 by 10 matrix. How big is capital Phi, the open loop system matrix, in this hypothetical system that I've given you dimensions for? How big is capital Phi? And Phi, the system matrix, is always square because it has to be compatible with the equations that it's in. And whatever ends up after forming the product of Phi with X, it has to be 10 rows tall, doesn't it? Because it's supposed to equal the left-hand side, which is just the state vector 1 time step into the future. And that's 10 rows of information. You know then that Phi X has to result in a 10-row output or response or result. And you know that phi x has to be compatible. X was 10 rows tall. Phi has to have 10 columns. Phi in this case is 10 by 10. 100 entries in phi. We'll have a few of those on the final. You'll have 2 minutes to enter all 100 entries in that system matrix phi. Do you see how these start to balloon or to get fairly large fairly quick? It's not that unusual necessarily to have a 10th order system, maybe. Now you have a phi matrix that has 100 entries. It's probably very sparse, hopefully, which means that it has a lot of zeros in it. But phi, the matrix, is 10 by 10. What's the gamma matrix, our input matrix, dimensionally? What are the dimensions on gamma? Do you remember what I told you? I said we had 10 states, 4 inputs, and 3 outputs. What is gamma dimensionally? How many rows does gamma have? Show me fingers. At the count of 3, you can fit all of these fingers in one response. 1, 2, 3. Somebody should be showing me 2 palms, right? You have 10 rows in gamma. How many columns do you have in gamma? Show me fingers at the count of 3. 1, 2, 3. So now I should be seeing all the fingers on one hand. No thumb. You only had 3 choices, didn't you? It could be 3, 4, or 10. I had 10 states, 4 inputs, 3 outputs. Gamma has to be compatible with U, which was 4 rows tall. So gamma is 4 columns wide in that hypothetical example. And I could draw that in a block diagram as below, and I'm just sort of indicating that that delay block is a bank of delay blocks. I may not do that all the time. I may just say there's my delay. But that's now effectively 10 delay blocks, because all of this is in vector matrix notation. Is that clear? I now am taking each of these components of little x, and there's 10 of those in this hypothetical example, and I'm pulling those off and putting those into phi. That's this product right there. And I'm adding in this piece, which is right there, to make my x at time L plus 1. The output equation is just y is equal to hx, and that's on the right-hand side of that block diagram. That's your system, and I want you to, when you see either the block diagram or the state space representation, you can actually sort of see both. You're starting to think in terms of either of those representations. You can think both at the same time if you want, or I would like for you to be thinking that way. Here is this summary square of zero order hold equivalence from, we're still in April, barely. This was in March. This was the first part of March. This was 2 months ago. You've had a spring break since then, but I'm just giving you a reference date if you want to go back into the notes. This I simply circled, cut and paste, and put back in here. Ooh, and it even cut it off. That should be frequency domain in the bottom. But you should be able to go from continuous time state space to discrete time. That's just what we had up above, sort of. Today what we are going to talk about is going in a different direction. We're actually going to start with a capital G of Z and go back up into a state space representation. If you went down in terms of the state space matrices, phi, gamma, C, and D, you can obtain capital G of Z from your state space representation by that matrix expression. If you started with continuous time state space, you would have an A matrix and a B matrix, a C matrix and a D matrix. You could find the capital phi by just doing the matrix exponential, e to the AT, and you should be comfortable doing that. That's a review for the final. And gamma is this same matrix exponential, but now you have capital T replaced with a variable mu, and you're integrating each of those entries with respect to mu. And you can generate gamma, the input matrix. All of this is simply a repeat of what we've seen back in the first part of March. What we want to do now is TF to SS, transfer function to state space. We want to walk through an example of how do you start with a capital G of Z, a state space, a transfer function, and generate a state space representation. How do you do that? And you've maybe already done that for a continuous time system. Let's do that for a discrete time system. Suppose now that somebody gives you a G of Z that is equal to 3 times Z over Z minus 2. Now, before we even get too far into this process, can you already anticipate some of the matrices, dimensions that you will end up with in capital Phi, gamma, and H? What's the order of this system, capital G of Z? Second order, isn't it? So capital Phi should be 2 by 2. This is a scalar transfer function, meaning you only have one transfer function. You have one input and one output. The number of inputs is 1. The number of outputs is 1. Michigan is 1. Are there any states that start with Q? Quebec is 1. That's not a state, but it's a Q. Okay? It's 1. So your gamma is 2 by 1. Your H is 1 by 2. Let's find out what those actually are. This transfer function is just a way of expressing a relationship between the output and the input. That's this 3 over Z minus 2. Oh, is that system open loop stable? Is that system stable in the open loop? No, because you have a pole outside the unit circle. You have one at the origin. That's a good one. But all it takes is one bad one, and you have one. It's out at Z equal to 2. So this is an unstable system. You're going to have to do something to it if you want it to be stable. Let's now multiply the denominator. And I'm not sure that we've done this before. Let's go ahead in this particular way. Let's cross multiply. That's still in the frequency domain, but we can pretty quickly take that into the time domain, can't we? We can now say that this is little y of what? Can I use n's or should I use l's for my time index? Will it confuse you? Does that look correct? as a difference equation. This describes the dynamic behavior of your system in the time domain. Let me write that all on one side, meaning let me just go ahead and pull that input term over to the left-hand side of that equality and just say that I have y of L plus 2 minus 2y of L plus 1 minus 3u of L is equal to 0. What I'm trying to do is create a state space representation from this difference equation. And if you remember what we were wanting, or what one way of thinking of a state space representation is as a block diagram. If we had a block diagram, how many delay blocks would you anticipate need to be present in that block diagram for this particular system? 2. It's second order. You would expect 2 delay blocks. Now what I want to do is somehow figure out how do I interconnect those delay blocks, and it's all going to be in such a way that that would describe this dynamic relationship. And what I'm going to do in creating this block diagram is I'm going to say I'm assuming that I have access to the output at the present time and the input at the present time. And from those two pieces of information, I'm going to try to create a block diagram that describes this dynamic behavior. With that said, let me say that I'm going to say here is u at time L, and here is y at time L, and I have those available that I can play with. I'm going to start by saying, suppose that I have 0 coming into a summing junction, which really means this entire left-hand side I could be injecting into this left-hand side because it's equal to 0, isn't it? So effectively, I'm inputting this y at L plus 2 minus 2y of L plus 1 minus 3u of L into that summing junction. But I want to essentially end up, after I've done my processing or signal operations on that difference equation, I want to end up with y of L on the right-hand side. So I'm going to try to get rid of some of these terms on this difference equation, or in this difference equation, and I can get rid of this one by simply adding plus 3L to that entire thing, and I can do that by coming over here and saying, oh, I can actually add 3u of L to 0, and if I do that, do you see what happens if I add those together? Whoops. I'm running out of space. I end up with y of L plus 2 minus 2y of L plus 1. And where is that signal going to be? I started with 0 coming into that summing junction, which is really those 3 blue terms. I added to that 3u of L. What's going to come out of that summing junction? This black expression, y of L plus 2 minus 2y of L plus 1, and I could call that, let's say, what do I want to call it? Alpha 1. That's now coming out right there. Is that clear? What if I delay alpha 1 by 1 delay? Whoops. What is alpha sub 2? Do you see what that is? That's just a delayed version, and 1 step delayed of alpha 1. Alpha 2 now is y of L plus 1 minus 2 y of L. But I have access to y of L on the right, and I could simplify alpha sub 2 if I now add in plus 2 y of L to that, and I can do that by pulling off y of L. Whoops. And now adding in 2 y of L to that summing junction. And the result of that I could say is now this alpha sub 3, which is right there. And if I delay that by 1 delay, what do I obtain? Alpha 4, which is just y of L. I've now finished my block diagram. This block diagram, it's not very complicated, but that now satisfies this difference equation that I started with right there. The relationship between my input and output is the same in this block diagram as it is in that difference equation, which is the same dynamical behavior as capital G of Z. If I now found via block diagram algebra the transfer function between the input U and the output Y in that block diagram, I should obtain that same capital G of Z. But now that I have this block diagram, what can I do? Do you remember the strategy for finding a state space representation from an all delay block diagram? Do you remember what you do to create a state space representation? How many states do you expect to have? The same as you have delay blocks, correct? And you label the outputs of those delay blocks as your state variable components. Let's just label, let me see if I'm consistent with my notes. Let's label this output of the first or the rightmost state, let's call that x sub 1 of n. And the output of the leftmost delay block, let's call that x sub 2 of n. Is it clear then what this location could be defined as? If the output of that delay block, a 1-unit delay, whoops, why didn't you wake me up? It's really going to confuse you. Let's call these indexes of L. If I've done all my others with time indices L, let me call each of those outputs of those delay blocks x sub 1 at time L and x sub 2 at time L. Overloaded. That's the word or description that's used for if you have an argument in a function that maybe can be used many different ways. Capital K is now overloaded. We're using it in an overloaded fashion. Earlier this semester, capital K was a scalar, wasn't it? That was our scalar feedback. Now, in the last 3 lectures, we've overloaded K. K can be a matrix. Sorry. Things just kind of float around, and occasionally they'll surface. Where was I? Asking you that green arrow, what can we label that green arrow in this diagram? That's x sub 1 at time L plus 1, isn't it? That's just one time step earlier, I should say later in time, than x sub 1 of L. If that's true, then analogous to that argument, this should be x sub 2 at time L plus 1. And now you basically have your state space representation. You simply have to use those labels to create your state space representation. Meaning, we have x sub 1 and x sub 2 at time L plus 1, and that's the leftmost part of our discrete time state space model. X is now 2 rows tall, isn't it? It's just a 2 vector. It's 2 by 1. Now, from this block diagram, we can write down the right-hand side. We get visitors that come in and go out. Come in and go out. They didn't like what we were offering for a meal? No? Okay. Oh, you weren't sharing. Whoa, we're going to get a bad reputation, aren't we? Okay, so where were we? Sharing? Let's share the answer. What's this? This is now our phi matrix, which is dimensionally of what size? This is capital Phi. It's 2 by 2, isn't it? And it is post-multiplied by x sub 1 and x sub 2, or our state vector, plus our gamma matrix. What's the dimension of gamma? That's our input matrix. How many rows does it have? 2. It has to be compatible with the left-hand side, which is 2 rows tall. How wide is gamma? We only have one input in this particular problem, so it's 1 column wide. We just have one input. Now, we have 6 elements that we need to populate in those two matrices. 4 in our phi matrix and 2 in our gamma matrix. What's the 1, 1 entry in capital Phi? Good. I didn't know if you were wanting to use the restroom. Sorry. We were in school and we'd put up a finger telling the teacher we needed to use the restroom, right? So now it's either 1 or 2. Those are our options, right? What do we have? We have 2 here, don't we? Our 1, 1 entry in capital Phi is 2 because it needs to be whatever coefficient is scaling x sub 1 of L. That's what's creating the 1, 1 entry in capital Phi. And that's 2 in this case. Is it clear where that's coming from? This entry now is 2. If we try to complete the first row of our phi matrix, here is our phi matrix. This is our gamma matrix. This, I might say, is 2 by 2, and it has real elements. That's that R of 2 by 2. This is now made up of real elements, and it's 2 by 1 dimensionally. What's in the 1, 2 entry of capital Phi? Well, that's whatever is scaling x sub 2 and multiplying I'm sorry, it's scale, what is the scale factor between, or scaling x sub 2 that creates x sub 1 of L plus 1? Or does it even impact x sub 1 of L plus 1? And now my alphas are sort of messing things up, aren't they? Those alphas were just labels. Those aren't scaling factors. Is that clear? The alphas aren't scaling anything. Those were just labeling those signal paths. What scales x sub 2 at time L to create x sub 1 of L plus 1? Now again, you have a few options with your fingers. And this one's 1, isn't it? So now we need a 1 there. What about our 1, 1 entry in gamma? We want to know the input. How does that directly impact the input to that summing junction whose output is x sub 1 of L plus 1? Does the input U directly enter that summing junction as an input? Those summing junctions, you have signals going in and one signal coming out. The signal coming out of that summing junction is x sub 1 of L plus 1. All the others are the inputs. You've already accounted for both of those input signals, haven't you? One was just x sub 2 at time L. The other one was 2 times x sub 1 at time L. There is no direct connection with our input, U. For that reason, this entry is 0. What are the weights to create x sub 2 of L plus 1? What's the bottom row of capital phi? There are no state variable components coming back to make up any inputs to that summing junction. There's nothing from x sub 2 directly going into that summing junction. There's nothing from x sub 1. Those are both scaled with zeros. The bottom row of capital phi is now 0 and 0. Is there anything else going into that summing junction? There is a weighting on U, isn't there? And it's weighted by 3, which means that the last row of gamma is now 3. And we now have the dynamic behavior of our system in a state space representation. The only thing remaining is to write down our output equation. Which in general could have an input. Y at time L is some linear combination of the states, x sub 1 at time L, x sub 2 at time L, and the input, U at time L. And they could all be coming to form, in general, you might have Y, the output, looking something more like that. And you might have a bunch of signals coming in from x sub 1, x sub 2, and U, all scaled. But in this case, there's not a whole lot making up Y, is there? How do we write Y in terms of the matrices H? Did we even define what this guy was? This one we were calling H, weren't we? What were we? Oh, we have it somewhere back here. Oh, I called it C before, but that could be our controller. See how overloaded some of these parameters are? Sorry. Whatever you want to call this, let's call this capital J. It's not a complex number. I didn't want to go I because you might think that's the identity matrix, and it's not. It's just another matrix. What are populating, or what are the entries in this H and J? We comfortable with that? Now what we want to do is we actually want to introduce full state feedback. The concept of, we know this system right now is unstable. We want to introduce an input U that's some linear combination of x sub 1 and x sub 2 to change the dynamic behavior of this system. That's what we want to do with full state feedback. Full state feedback is saying that U at time L is now minus K x at time L, and if this guy is n by 1 and this input is Michigan tall, what are the dimensions on K? It's now in general a matrix. And what are the dimensions on this matrix capital K? It has to be compatible with X, doesn't it? X is hitting it on the right. X has Nevada rows. K has to have Nevada columns. We know that this K is now something by N. And K has to have the same number of rows as U has. U has Michigan rows. K is now Michigan by Nevada, M by N. Is that clear? Now, if we go back to our example that we just came from, how big is K? How many rows tall is K? It's as tall as we had number of inputs. How many inputs did we have in that example? We just had one input. K is one row tall. I already gave it away by putting that bracket, not very tall. How many columns wide is K? It's as wide as our state vector is tall. We had two states, so we could think of this as K1 and K2. This is now 1 by 2. This is the number of inputs. And 2 is the number of states. Our objective is we want to find those coefficients, those variables, K sub 1 and K sub 2, to change the dynamic behavior of our system. We want to find K and when I say capital K, I'm actually meaning these two coefficients or variables, K sub 1 and K sub 2, to change the dynamics. If you wanted to see this in a diagram, let's look at our block diagram. Maybe this is an easier way to think about it if you're having trouble seeing what's going on with the matrices. Here is our drawn just a little differently than what we had before. this output we labeled as x sub 1, this one was x sub 2, and we are now saying that we want to take x sub 1 and scale it by k sub 1, and k times x is going to come back and make up all of u. So we now take x sub 1, we scale it by k1, we change the sign because we're saying minus, and all of that is going to make up part of u of l. U of l is going to be minus k sub 1 x sub 1 minus k sub 2 x sub 2. Is it clear what that block diagram is doing? Now we have at our disposal k sub 1 and k sub 2. We're going to change those in some way to change the dynamic behavior, and obviously we want to stabilize the system. Do you see what we're doing differently than what we've done before? Is there anything jumping out at you here in this block diagram that looks a little different than what we did in previous control strategies? What were we accessing or measuring or assuming we had available in our earlier controllers when we were controlling or creating these capital C of Z's, these transfer function based controllers? What were we assuming we had available or that we could measure? What was always our feedback? We were always just assuming a -1 in that feedback path, weren't we? The output was all we were measuring, and we were putting all of our controller, all of this manipulation of the air signal to inject into our input U was all coming from the output Y and comparing that to a reference input. Now what are we doing? Now we are assuming we can go in internally to our system and measure directly the states, x sub 1. We can measure x sub 1, scale it by k1, and feed that back to create the input U. Go in internal to our system and measure x sub 2, that state, scale it by k sub 2, and allow that to also influence our input. We now have two signals, because we have two states, that we're measuring, scaling, and using to feed back to create our input U. That's quite a bit different than what we were doing with transfer function-based controllers. Is that clear? Or at least you maybe see the distinction? Let's now figure out how we can relate this block diagram, this structure for full state feedback, into a strategy for selecting these gains k sub 1 and k sub 2. We have our original system, and here I'm going to not expand on how tall x is. It's now a vector x. That's phi x of L plus gamma u of L. And now I'm going to say, let me create or use full state feedback. U of L is now minus k x of L. If I use that U in there, now I can start to try to see what's going to happen to my system. X at time L plus 1 now becomes phi x at L plus gamma times minus k x of L. But gamma is a matrix, K is a matrix, and that minus sign I'm simply going to, I'm doing this in maybe a lot of steps so that you don't get lost as to where everything is coming from. X, the state vector, is common to both of those terms on the right-hand side. Let me factor it out. And now I hope you can see that I've changed the dynamic behavior of the system. I've moved it from an open loop system matrix, capital Phi, to a closed loop system matrix. I'm going to call that capital Phi sub C. This is now the closed loop system matrix. And that's going to be a function of these unknown coefficients, k sub 1 and k sub 2, and I want to select those in a way that changes my capital Phi sub C to more desirable system behavior. Capital Phi had poles, which are the eigenvalues of Phi, one at the origin and one at 2. Remember where our poles were in our capital G of Z? The poles of our open loop system were at the origin. We had Z times Z minus 2. That's the same as the eigenvalues of capital Phi. Capital Phi would have eigenvalues at the origin and at 2. We want to now locate the eigenvalues of Phi sub C in a more desirable location. And we know where that is. It's inside the unit circle. And we know maybe where we want that based on our understanding or knowledge of second order systems. If we go back to our example that gives us numbers, we can now say that Phi sub C is Phi minus gamma K. In terms of matrices, Phi was 2, 1, 0, 0, going row-wise. Gamma was 0, 3, and K was a 1 by 2 matrix. If you multiply the two matrices on the right, we get 0 in the top row, since 0 is weighting K1 and K2, and 3 scales the bottom row. I'm going to do that multiplication and subtract it from Phi so that I end up with 2, 1 upstairs, and I have minus 3K1 and minus 3K sub 2 in the bottom row. I'm really interested in the eigenvalues of that closed loop system matrix because that tells me the dynamic behavior of my closed loop system. And I can find the eigenvalues of a matrix by looking at Zi minus capital Phi sub C's determinant. Let me now look at the eigenvalues of that closed loop system matrix. Let me call that delta sub K of Z. That's now the determinant of Zi minus Phi sub C. Or, I'm going to write this out in a lot of detail. The vertical lines represent determinant. I have Z times the identity matrix, and that identity matrix needs to be the same size, or it needs to be compatible with the capital Phi sub C. Capital Phi sub C was 2 by 2. My identity matrix is a 2 by 2 identity matrix. And now I subtract Phi sub C. And Phi sub C was 2 minus 3K1. Now I'm reading column-wise. 1 minus 3K sub 2. And I need to compute the determinant of that combination of variables. Z is my complex frequency variable. I have in the 1, 1 entry of that 2 by 2 matrix, I now have Z minus 2. In the 2, 2 entry on the diagonal, I have Z plus 3 K sub 2. And in the off diagonal, I have 0 minus 1 in the 1, 2 entry. And in the lower corner, left-hand corner, I have 0 minus a minus 3K1, or just a 3K sub 1. Here we only have to know the determinant of a 2 by 2 matrix. Maybe on the final you'll have to find the determinant of a 10 by 10. But a 2 by 2 determinant is product of the diagonals minus the product of the off diagonals. If we do that here and keep track of our variables, I have Z minus 2 times Z plus 3K sub 2 minus a minus 1 times 3, K sub 1. Or I have Z squared plus a minus 2 plus 3 K sub 2 times Z plus 3K sub 1, and I need this piece, don't I? Which is minus 6 K sub 2. Did I do the multiplication right or correct? Now what I want to do is figure out how do I choose or how do I select K1 and K sub 2. Now I know how they influence the coefficients in this second order expression. You know the roots of a quadratic. That's what you're interested in. Now what we want to do, let me just try to explain this verbally in case we run out of time. I want to create a desired second order polynomial. And how am I going to find that? My desired characteristic polynomial is going to be where I want my closed loop poles to be. And you know where that might be based on settling time, percent overshoot, and peak time. Your heart, your bullseye, and your angle. You know how to pick those deltas. You find a delta, a combination of deltas, that will give you a desired polynomial. You can now equate those desired polynomial coefficients with these coefficients here that are expressed in terms of K1 and K2. You have two equations, two unknowns. You can solve for K1 and K2. And those are then your feedback gain elements in this block diagram that will change your closed loop behavior to produce dynamics consistent with your desired closed loop poles, which were your heart, your bullseye, and your angle. Your percent overshoot, settling time, and peak time. Let's do that. Here is this process for designing what I will call designing K. Or you could say, what is this process for finding this unknown full state feedback gain matrix, capital K, which in this case is 1 by 2, or there's two entries that I need to find. In our example, K, the matrix K, was just K1, K2. The process now, I'll just make it into a few steps. Step 1 is decide on a desired set of closed loop poles. Or closed loop pole locations. In our example, how many closed loop poles do we have? 2. It's a second order system. I'm just going to pick those somewhat arbitrarily, but I hope that you appreciate the fact that I could make your final exam one question with 15 parts. Just saying. Meaning I could now say, I want your closed loop poles to have a particular settling time, rise time, percent overshoot, and that would give you your Z delta. Here I just pulled them out of the air. And I want those to be in complex conjugate pairs, so I need plus and minus J 0.2. What if you had a fifth order system? Since on the final I've sort of indicated you might have a 10th order, let's just talk about a fifth order. What would you do if you now had a fifth order system and you needed to find your desired polynomial? Where would you locate your poles, your desired closed loop poles? Inside the unit circle, I'd have to accept that answer. But here you might say, oh, let me pick 2 that are dominant based on the heart, the bullseye, and the angle, the percent overshoot, settling time, and peak time. That's my dominant. And then my other 3 leftover poles, let me make them really fast. Let me just put them at the origin. I have 3 poles at the origin and 2 that are dominating the response. There's your 5 poles. Is that clear? If you had a 10th order system, you would, for this class, you would say, give me 2 dominant and the remaining 8. Let me pick those and put them at the origin. Now you have Z to the 8th times this quadratic. Those are your 10 poles. Once you've decided on where your closed loop poles are located, then you need to create the desired characteristic polynomial with all of these desired closed loop poles. And let's call that now, this is need to be a little bit neater than that. Let's call that delta sub D for delta desired of Z. That's my desired characteristic polynomial equation. In our case, if we return to our example, delta sub D of Z is now Z minus 0.8 plus J 0.8 times Z minus 0.8 minus J 0.2. Do you see where that came from? I'm just creating polynomials that, well, if I would have subtracted, maybe I'll do that. Let me change this. Let me subtract. The first factor is the pole in the first quadrant. The second factor corresponds to the conjugate of that, which is the pole in the fourth quadrant in the z-plane. Whoops. Wondered why everybody was giving me a questioning look. I corrected one and didn't correct the other. Okay? Those have to be conjugates of each other. Now, if you multiply this out, because of the way we selected this, I'm doing this sort of on purpose, you have z minus 0.8 squared. Do you see that the cross terms cancel because of the plus and minus j? And then you have the product of the outermost entries. So you have minus j squared, And j is the square root of minus 1, so minus 1 j squared is just plus 0.2 quantity squared. That's why you'll see me writing these quadratic poles that are complex conjugates in this form. Z minus something, the real part squared, plus the imaginary part squared. That's where that's coming from. Now if we multiply this out, we end up with z squared minus 2, 0.8z plus 0.8 squared plus 0.2 squared. Or this is now z squared minus 1.6z plus 0.64 plus 0.04, or this, our desired characteristic polynomial as a function of z, is now z squared minus 1.6z plus, what in the world, that I think is not really a point. I didn't think so. It was just where I picked up my pen. 0.68. That's my desired characteristic polynomial. I now want to do the final step really in this process for finding these unknown k's. I want to equate this desired polynomial with my characteristic polynomial in terms of the k's. Equate coefficients in the two polynomials to find your K matrix, and in our example. So really, this is now what I'm suggesting is you take delta sub K of Z and set that equal to delta sub D of Z, compare coefficients, and solve for the unknown K's. In our example, we now have delta sub K of Z was Z squared minus, or plus, minus 2 plus 3K sub 2Z plus 3K1 minus 6K sub 2, and we want that to equal Z squared minus 1.6Z plus 0.68. Where this blue term, or blue polynomial, was our desired characteristic polynomial. The black polynomial was our polynomial in terms of the unknown k's that we didn't know what values to use. Now you simply equate coefficients. If you equate the Z1 coefficient, now we have minus 1.6 is equal to minus 2 plus 3K sub 2. Good thing I picked that first. That's one equation and one unknown. I can now say that 3K sub 2 is 2 minus 1.6, or K sub 2 is equal to 0.4 divided by 3. Is that right? K sub 2 is now 0.133 with a repeating 3. If we equate the constant coefficient, or take 0.68 and set that equal to 3K1 minus 6K sub 2, and we've already luckily found K sub 2, we now know that 0.68 is equal to 3K1 minus 6K sub 2. And if we solve that, whoops, we're running out of time. Does everyone understand what we're doing? We've already found K2. We plug that in. K1 ends up being 0.4933. You can put that back into your block diagram, or you can say that the K matrix full state feedback to produce closed loop poles at 0.2 plus and I'm sorry 0.8 plus and minus J 0.2 is found by this full state feedback gain matrix K. You can go back to your block diagram and see where those K's feed back and how that now changes your closed loop dynamics. You've now converted an unstable system to a stable system where you put those poles almost wherever you wanted because of full state feedback. And we'll show that the system must have been controllable and how to inject a reference input on our next meeting. We'll pick up at that point next time.